Part A asks to determine the empirical formula of the hydrocarbon. So you use the given 6 grams of carbon and the given 1.344 grams of hydrogen and get them both into moles. And that gives you 1/2 moles of carbon and 4/3 moles of hydrogen. And if you multiply both by 6, that'll get them to a whole number. And you would round the 7.98 to 8, and that will give you C3H8. B asks to calculate the molar mass of the hydrocarbon. So to do that, you do density times the R constant times temperature over pressure, and all are given, so you just plug and chug, and you get 43.97 grams per mole. And the second part asks to determine the molecular formula, and the ratio is the empirical weight to the molecular weight, and that's about 1, so the molecular formula is the same as the empirical, C3H8. Part C asks for the value of change of HF for C7H16. So you would take the given kilojoules equals the coefficient of H2O in the reaction times X minus the given kilojoules per mole for H2O plus the 7 coefficient of CO2 times the number of kilojoules per mole given in the chart. And once you solve all those numbers and add and subtract, you should round to 191 kilojoules per mole. Part D, you calculate the amount of heat released to the calorimeter. So you would just take the 0.0108 mole sample that was combusted of C7H16 times the kilojoules of C7H16 given over 1 mole, and that's negative 52.38 kilojoules. And part 2 says, given that the total heat capacity of the calorimeter is 9.273 kilojoules per Celsius to the -1, calculate the temperature change of the calorimeter. And to do that, you would do the number you calculated in part 1 times 1 degree over the 9.273 kilojoules, and you should get 5.65 degrees Celsius.